a vector is, right? If my kid loves used to watch it like every day. The bad guy vector, right? A directed line segment, that's really how you can say it's a vector. But no one's going to quote the movie from a vector. A vector is a line segment that has both direction and magnitude. That's what the guy's saying. Direction and magnitude. So a vector has direction, which just means that it tells you which direction it's going. And magnitude is just another word for length. So I'll put underneath there, length. Which if it's a line segment, then you could measure it. That's the part that's not really new. A line segment always has length. But with the vector, it's going to have an arrow on it telling you which direction it's going in. So this is just an example of a point. If we've always graphed, we can call that XY as opposed to AB, but your book calls AB. That same point out here, if we draw the line and put an arrow on it, we can now say that that is a vector. And we label the components of a vector. Instead of ordered pairs, we use these little pointed parentheses. I don't know the official name of them, so I call them pointed parentheses. But it's not really that scary because we're just changing from parentheses to pointed parentheses. And we're just putting an arrow on it to show that which direction it's going. So far, so good, right? So we can talk about many-dimensional vectors, three-dimensional vectors. I took a grad class last semester, and we talked about like five-dimensional, and like what does that even mean, five-dimensional at that point? I don't even know. But like it could be any dimensional. We're going to focus on two-dimensional vectors, all right? So we're going to say that a two-dimensional vector is just an ordered pair of real numbers, right? Wherever that line segment is. And we're going to write it in component form. So kind of some new vocab here as we talk about this. And the component form is the same as the ordered pair form. It's just with the pointed parentheses. And we call it component form because each one of those is called a component, and that's what that says. The numbers A and B are the components of the vector. The standard representation of the vector is those pointed parentheses. And when you see that, that's measuring from the origin to that point. And so it's really easy to graph it because you just graph it like any other point that you've ever graphed it. And then the magnitude is just a fancy word for length. Just how long that line segment is, and I'm going to show you how we can derive that to do it. And the direction is just which way the arrow is pointing. And then the origin or the vector 0, 0 is called the zero vector. And it has no length and no direction. And so they made this bold. A lot of times the way they say a vector, like if we want to call this a zero vector, is you could just draw a little arrow above it. And sometimes they just draw like the half arrow up. I don't really know why. But like you can draw the whole arrow that way, or you can just be fancy and draw a little arrow above it. And that's read as the zero vector when you see it written. So let's look at the vector that starts at the origin here, all right? So this vector starts at the origin, it goes up to 3, 4. So very easily we could say the component form of this vector is just 3, 4. Because it starts at 3, 4, because it goes up to that point. Think about if I wanted to find the length of that. I'm going to give you a formula to that in a minute, but I just want to kind of show you where that comes from. if I wanted to find the length of that, could I draw a line down there and make a triangle? And I've made a right triangle like we've been dealing with pretty much this whole semester. This is just the hypotenuse of that. So think about how long this is going to be. Well, that's just up 4, so that's the length of 4. This one is the x-coordinate, which is a length of 3. So to find the hypotenuse, I'm just going to do Pythagorean theorem, but you can kind of think about if you know the points or you know the component form, all you have to do is take the square root of adding those together, because that's like your a squared and your b squared, and I think on the next slide I have that formula for you, but I just want to show you that's where it comes from. So if I wanted to find the magnitude of this, I'm just going to take the square root of 3 squared plus 4 squared, which this one works out really nice, right? That's just 5. Which means that that vector has a length or a magnitude of 5. So, initial point, terminal point, and equivalent vectors. The initial point is where the vector starts. Initial point, where vector begins. We really like our vectors to start at the origin. We're going to deal with this one that doesn't in a minute and figure out how to get right into component form. So most of the time our vectors are going to start at 0, 0, otherwise, but that would be my initial point. And then the terminal point is just where it ends. And if it starts at the origin, then that terminal point are just your components. So the terminal point is where vector starts. Kind of just like an angle, we have the initial ray and the terminal point. And then equivalent vectors, they have to have the same things, which means they have to have equal lengths or magnitude, and they have to be in the same direction, because the vector has 2 parts. So, do you agree that this segment is in the same direction as this segment? Is that true or not true? Yes, we can put them in the same direction. Pointing the same way. I think it's in the same direction. Which means we need to see if they have the same lengths. So we need to know, how do we take this and we write it so that it looks like it's starting at the origin, like the component form, like if I moved it over. So we need to, I think we need to, looks like. So if you have a vector that's made by 2 points, one not being the origin. So a vector made with like x1, y1, and x2, y2. Right, so instead of starting at 0, 0, where you can just say that's the component form, find the component form to change to those pointed arrows. You're just going to subtract the terminal x-coordinate from the initial x-coordinate. So you're just going to take x2 minus x1 to get the first point, and y2 minus y1. Totally the distance formula without the square root, right? But yes, when you do the distance formula, if we wanted to find the length of that, that's what we totally could do with the distance formula. And you're going to see on the next slide they give you the distance formula. So if I was going to find the component form of this vector, that would just be -1 minus -4 and 6 minus 2. Which means, look what the component form is. It is just 3, 4, which means if the component form of this is 3, 4, and we know this component form is 3, 4, then they're going to have the same length, because now we know they're going to have 5 to come to that. And so that's kind of an important thing to know how to take something that's not starting at the origin and write it in the component form. Which you can see, you get the same thing here, right? If I took 3 minus 0 and 4 minus 0, there's no need to subtract from 0. So that's yes, because if it starts at the origin, then wherever that terminal point is always just the components, because when you subtract that's a lot on that slide. So, kind of jump the gun on the magnitude stuff here, but magnitude, I'm going to put equals length. And just like Jarrett said, that if you have 2 ordered pairs to find the length of it, you can totally just do the distance formula. What's really nice is if you have it in component forms, and then you can kind of skip a little bit. But that's what this says here, right? The distance formula, 2 ordered pairs of a line segment, is just the square root of subtracting the x-coordinate squared plus subtracting the y-coordinate. Just like we showed on the last example, if it's in component form already, and you know what A and B are, then you know, the other one's 0, so it's kind of like just taking the 0 out of here. It's just the square root, I don't know why there's no square on it, of A squared plus B squared. I think we did this already, so I don't think we can do number 1. Because we found the magnitude already, but we can do it again if you want. That the one, they both are going to have the same, because they both have component forms of 3, 4. So the magnitude, notice they put absolute value bars around it. I don't really know that those are absolute value. I mean, obviously links can't be negative. In my Math 137 book, the symbol for magnitude is double bars like this, and that's what's in my grad book that I took. It was double bars, but in our book they just use 1. But it just means the magnitude of the vector, and it would just be the square root of 9 plus 16, which we said is 5. Magnitude is length, which should be a number. If it was a square root, I don't want a decimal, right? Leave it as an exact, just like a square root is. Okay, so part of your homework today is just going to be writing in component form and finding magnitude. I think that's the next example. So it says find the magnitude of the vector V represented by the line segment PQ, where P is 3, negative 4, and Q is 5, 2. You have choices here. You could just do the distance formula, and that would give you the magnitude. Or you could find the component form first, and then just do the square root. Same answer, so it's just whichever one you feel more comfortable with. Just know that sometimes they're going to give you the component form. You're going to know how to do that. So I'm going to do both, just so that you have that in your notes. So they're calling this V, so I'm going to say the absolute value, the magnitude of V. That's how we should do that. If I just use the points, distance formula is just the square root of subtracting the x's squared and squaring it. It really doesn't matter which one you start with, but I'm going to start with Q, like it says here. So 5 minus 3 squared plus subtracting the y squared, 2 minus negative 4 squared. Minus 3 is 2 squared, 4 plus 2 minus negative 4 is really 6 squared, which is 36, which is the square root of 40. I don't want you to leave it like that, right? We could break that up as 4 times 10, which means 2 squared of 10 would be the answer you could give me. If the question made you put it in component form anyway, I'm going to do it that way too. So vector V in component form would be subtract the x's. You have to start with the terminal x coordinate first. So you have to do 5 minus 3, 2 minus negative 4. So component form there would be Yeah, that's just the distance formula of a line segment. So both of these are magnitude, right? This is magnitude. I'm going to find the magnitude here again in a minute. But when you do it like this, it's just ordered pairs. So it's not anything different. It's just taking two ordered pairs on a line segment. This is called component form. So now to do the same thing, you're going to see I get the same answer because I've just already subtracted the x's. If it's in component form, I can just take the first component squared plus the second component squared, which is just going to be 4 plus 36, which is still the square root of 40, which is still 2 square root of 10. Definitely this one looks like less work, but you have to do the subtraction over here. Like either way, you're subtracting x's, so I just don't want you to feel like you have to do one or the other. I feel like you should be comfortable with both, because it just depends on what question they ask. Questions about that? Is it terrible? It's just kind of getting used to the new notation and the new words that come up along with it. Adding and subtracting is also really simple. It's just making sure you understand what it's saying. So vector addition and scalar multiplication. So if you have two vectors, notice in component form, they just called one u, so its components are u1, u2, and v1, v2. And then we'll get to k in a minute. K is a scalar. It just means like multiplying a number in front, not multiplying by another vector, but just multiplying it by a number. So it has its own special word for that, scalar. Kind of a nice word to know. I don't know why they use resultant, but the resultant vector is like the result you get when you do an operation. You add or you subtract. So again, just kind of be aware as you're reading when you see those words. It's just kind of getting used to what it means. It just means what you get when you add them together. All you have to do is add the corresponding components. So to add vector u plus vector v, it's easy. All you're going to do is add u1 plus v1. That's going to be your new first component. And to get the second component, you're going to add u2 plus v2. And if it was subtraction, you just subtract. Ways that you can think of showing this geometrically, not that you're ever going to draw it geometrically, because why would you add them? So just to kind of show you, if I had vector u going like this, and I had vector v going up like this, if you want to add them, you can kind of think about making a parallelogram using u and v to kind of copy. And the resultant is the diagonal of that, which is kind of, it's called the parallelogram method. So my drawing's not great, but pretend I'm going to draw another u starting here and just going across. So it should be slanted the same. I'm going to take this and put it up here, right? Make a little parallelogram. And if I took this one and move it over here, you can always make a parallelogram because a parallelogram have opposite sides that are congruent, parallel. And when you add two vectors that both start at the same point, the sum is the vector that makes the diagonal there. So the vector here, that would be your resultant, which gives you your u1 plus v1 and u2 plus v2. You're not. I'm not in this class. It's just sometimes if you were looking at a graph, you could see if your answer made sense, if it's in the right area. Obviously, think about if they're going in opposite directions. If you add a vector that's exactly the opposite of another, then the middle of that, the diagonal, would be like 0, so they can cancel each other out, which that can happen. Also a triangle method. I won't bore you with it, but it is in your book if you'd like to read about it, if you're interested in that kind of stuff. The scalar is even easier. I'm going to draw the picture first. So think about if I had vector u. What do you think 2u would look like? You just add on another u, the same length, the same direction, right? And you can think about that's u and u, which gives you 2u. So when you have a number, a scalar, multiplied times some vector, all you're going to do is multiply the components by that scalar. So we can say if you have k times vector u, that's the same as the component ku1 and ku. There's a big list of properties of vectors in your book that you're welcome to look at about like unit property and all that stuff. A nice table that you can check out. So let's just look at an example here. I decided to combine scalar and addition all together, right? So it says, again, notice the pointed parentheses let us know they're in component form. Let us know that those are starting at the origin. And it says find 3u plus v. Just like everything you've ever done, order of operation applies, which means you have to multiply 3 times again before you can add the things together to do that. So I'm just going to kind of show my work here. Probably you could just jump straight to the answer. But 3 times u would be 3 times the vector 2, -1. And then I'm going to add that to 5, 3. And again, not hard math. Nothing like the proofs you just have to do on your test. But you just have to kind of get used to the new notation and make sure you're using pointed parentheses. So this would just become 6 -3. And then I'm just going to add the corresponding parts. So 6 plus 5 is 11. And -3 plus 3 is 0. Questions about that? That's like basic, what is a vector? What does the magnitude mean? Add, subtract, stable. From there, we want to add on, what can we do with vectors? That's kind of what we're going to kind of build up today, so that tomorrow we can actually do some stuff with vectors. So just like we have the unit circle with vectors, we like unit vectors, right? So a unit vector is a vector with magnitude equaling 1, right? This is our notation for magnitude. So when it has a length of 1, we like that better. So we're going to make things into unit vectors that aren't unit vectors, all right? So if you want to find a unit vector, notice you can't do it with a 0 vector because you can't take something with a length of 0 and make it a length of 1. So the 0 vector's out. But if you have a vector u and you want to turn it into a unit vector, here's your formula. You're going to take 1 over the magnitude. So the unit vector equals 1 over the magnitude, I'm going to say, of v. Okay. If v is not the 0 vector, then its unit vector equals 1 over the magnitude of v times the vector. Or another way to write that is 1 over the magnitude times the component form v1, v2. Which means that's just a scalar that you can multiply in. I'm going to show you how this works. I will tell you that a lot of times you get not great answers. Like they look ugly. They're going to be fractions because your magnitude isn't so nice right now. Okay? So look at this one. Find a unit vector that's in the same direction as this. So we're not going to change the direction. We just have to change its length, which means we have to change the components. So step 1 is we need to find its magnitude. Okay? Find magnitude. So my magnitude is the square root of multiplying these together squared, so that would be 4 plus 9, which is the square root of 13. So right now this vector does not have a length of 1, it has a length of 3. Step 2 is we're going to use our formula. We're going to take 1 over the magnitude times the vector. Which is just going to be 1 over the square root of 13 times the vector 2, negative 3. So let's just multiply that in. So that just gives me 2 over the square root of 13 and negative 3 over the square root of 13. Rationalize those, but I'm okay, we'll leave it like that. This would be a vector that now has a length of 1, and you don't have to actually do this, but let me show you why this works to divide by the magnitude, because now, if I found the magnitude of this, think about what that would be. On the top, I would square that, that would be 4, and the square root of 13 squared is just 13, and on the second one, that would be 9 over 13. So what happens is we still get 13 on the top. By dividing by that, we now are just going to get 13 over 13, which gives you a length of 1. So it's kind of a really cool little formula of how you can put stuff to unit vectors. Right? So that's a formula that you're going to do. All right. Let's keep going. Lots of stuff. So the reason that we have to change things to unit vectors is because we want to be able to write them in unit vector form. So there are 2 special unit vectors, and they're just the unit vectors that would occur on the x and the y axis. So think about this. If I had this, and I drew 1 unit to here, right? That's a unit vector on the x-axis. That's the unit vector we call I, not the imaginary number, just the I vector. And then if you go 0, 1, right? That would be the vector straight up on the y-axis that has a length of 1. That's the unit vector j. What we like to do, right? We can write vectors in component form. We also like to write them in form of I and j. So let me kind of show you where this comes from. It's kind of like a proof. And then once I give you the proof, we can just use it. So they use A and B. I don't like A and B. I'm changing it to B1, B2, the way that we've been kind of doing it already. So I could separate this into 2 vectors, kind of using our rule of addition. Like I could write that as B1, comma 0 plus 0, comma B2. Do you agree if I added that together, that would just equal back to my unit vector, my regular vector? It's B1 plus 0 is 1, and 0 plus B2 is 2. Trying to get to a point here. So then, if I pulled the V1 out, right, as a scalar, I could write it as V1 times the vector 1, 0. Plus, if I pulled the V2 out, that would be V2 times the vector 0, 1, and a reverse scalar multiplication. Again, kind of think about what happens. If I multiply that back in, V1 times 1 is V1, V1 times 0 is still 0, so it's still the same thing. But I'm trying to get to this where this I and j come in. So every time you have a vector, you could do that, which means to write it in this ij form, I could replace 1, 0 with I, which means we could write this as V1I plus V sub 2 and 0, 1 is always j. Again, you don't have to do all that work every time because you can just see that every vector can be written as just V1I plus V2j. Which means if you know the components, all you do is you put 1 in front of I, and then you add the 1 times j as well. But I just wanted to kind of show you why we do that, where it comes from, not stand up. So component forms used a lot. You're also going to see I, j forms a lot. And so they might give you a question and just ask you, you know, like instead of adding it in component form, it might say like b equals 2i plus 4j, and vector w equals 7i minus 6j. And then they just might ask you to add those. And so you're going to add those by just adding the components just like we did before. Really easy. If you wanted to change it to component form, that would just be the component to 4. This would just be the components 7, negative 6. So if I added b plus w, I can just add the i's, which would be 9i. 4 minus 6 is negative 2j, which you can see is the same thing, that I would get 9, negative 2 here. So just know that component form, ij form, they can go back and forth, and you're going to be working with both of those. All right, ready for the trig? So I can do vectors. The trig. I just broke them up, right? So like I just am doing a proof, and I'm just breaking it up so I can get to this point. So like it's not, like I just broke this up so that I can get to this. But do you agree that if I added those together, it does equal this back? So all I did was I just broke it up just like if I had the point 3, 4, not even a vector, just a point, then I can break that up as 3, 0, plus 0, 4, just saying that it's, so it was just kind of a step in my proof, because I needed to get this. One of those hard things about proofs is I just did it for a second. Okay, so a lot of your homework is just kind of working with vectors, and then where we're going to kind of pick up tomorrow is where we're going to leave off today. Talk about the tree. So again, maybe we should write up here our vector. Vector b is component form b1, b2, or is ij form b1i plus b2j. So what if they give you an angle and you need to find the components of your vector? So it says if B has direction angle theta and the components of B can be computed using this formula. I want to maybe show you where this formula comes from. Let me give you this and then I'll show you where this comes from. So notice that we're taking the magnitude of V times the cosine of the angle as the first component, and the magnitude of V times the sine in the second one. It should be easy to remember that cosine should come first and sine should come second, since cosine is x and sine is y. Really easy to show you where this comes from. If we draw a lovely picture here, and I draw a vector in here with v1, v2, right? It's all about a triangle. I draw in my triangle. This is my theta. Only difference is we're not using x, y's, and r's here. We're going to say this is my magnitude, so this is my absolute value, my magnitude of v. This is my y value, which I'm going to say is v sub 2. This is my x value, which is v sub 1. So if you couldn't remember this formula, all you have to do is set up the ratios here for sine and cosine. If I set up sine of theta, look what I would get. Sine of theta equals y over r, or v sub 2 over the magnitude. Notice they're solving for v sub 2, right? This is v sub 1, v sub 2. So all they're doing is multiplying that over. You multiply both sides by the magnitude, you get the magnitude times sine equals v sub 2. So again, not a made-up formula, but just using the trig that we've been building on all semester. And you could do the same thing for cosine. Cosine of theta equals v sub 1 over the magnitude, which means if we solve for v sub 1, we would get that formula. Again, if we wanted the unit vector, if we wanted a magnitude of 1, right, our formula is the vector divided by its magnitude. But if its magnitude is 1, right, if this is 1, then it's just what we've known all along about x and y, right? It's just cosine and sine. It's just xy on the unit circle. So again, that's why we like the unit vector, because it kind of corresponds directly with our unit circle. What are you confused about? You're confused where this, like this? Because I'm just labeling, instead of x and y, right? I can make the exact same picture the way that we've done, where this is x and this is y. This is our y, this is our x, this is our r, right? The only difference is instead of using x, y, and r, I'm using the ordered pairs v1, v2, and I'm using the magnitude. But it's the same ratio, right? We know that sine of an angle is y over r, or in the unit circle, that's just y. You just have to change it to the v1s and the v2. So it's just v2 over your magnitude. You'll have to find the magnitude, yes, given a point. Yes. So, hold on, don't leave, because I don't know that we're doing all this homework yet. I'd like you to try all the homework, just because you have all the formulas. There's a lovely example. Example 5 in your book is the one example that we didn't get to that gives you an angle and a magnitude. So on that one, Maddie, they give you the magnitude.
Technical students, the upper please. Evan Steffi, David Johnson, Logan Taylor, Michael Lauermore, the upper please.
So starting at 30, 33, and 36, there's only 2 are like example 5 in your book. Please look at them because it's not that bad to do, okay? Yeah, welcome to precalculus.